In today's lecture, we're going to be covering optimal control and the algebraic Riccati equation. Now, as a reminder, what we covered in our last lecture was calculus variations. With calculus variations, if I have a cost function, I can find the path that minimizes that cost function. Any function that minimizes a functional has to satisfy the algebraic Riccati equation. Today, what I'd like to look at is how does that apply when you have a dynamic system? For example, suppose I have x as a function of time, and I have a cost function. I want to minimize x squared and minimize its velocity. Subject to the constraints, I want to go between at t equals 0, it's at 5. At t equals 8, it's equal to 4. To solve that equation, I plug it into the algebraic Riccati equation. My functional is x squared plus x dot squared. The Euler LaGrange equation is the partial of f with respect to x minus the full derivative with respect to t times fx dot equals 0. Plugging it in, partial with respect to x is 2x, partial with respect to x dot is 2x dot, and I take the full derivative, and I get x minus x double prime equals 0, where I factored out the 2. What that means is, using LaPlace notation, 1 minus s squared x equals 0, which either means x equals 0, that's the trivial solution, or s is plus minus 1. And that's very common in this type of problem. I'll have an unstable and a stable eigenvalue. S is being plus or minus 1 means the general solution of x of t is in this form. Plugging in the endpoint constraints, at t equals 0, x is 5. At t equals 8, x is 4. Gives me two equations, two unknowns, solve for a and b, and you wind up with this being the optimal path. This is the optimal path between 5 and 4 in 8 seconds, where the cost function is x squared and x dot squared. Now note, or second example, suppose I have a dynamic system. My dynamic system is x dot equals u, and I want to minimize a cost function. I want to force x to 0 quickly, and I want to keep the fuel usage small. So I'm going to weight x squared and 9u squared. And 9 is just kind of an arbitrary constant. We're just going to assume 9 for now. I also want to have a constraint. I want to do what we did before. At t equals 0, it's 5. T equals 8, it's 4. Go from 5 to 4 in 8 seconds, while minimizing x squared and minimizing the fuel. To solve that, I add a LaGrange multiplier. These dynamics solve backwards to get x dot minus u equals 0. I can always add 0 to a function and not change anything. M is my Lagrange multiplier. I now have a function of x, u, and m. To solve that, I need to solve three Euler LaGrange equations. Do the Euler LaGrange equation with respect to x, the Euler LaGrange equation with respect to u, and the Euler LaGrange equation with respect to m. All three of these have to be satisfied. If you do some substitution to get rid of m and get rid of u, you'll wind up with an equation in x. Turns out in this case, the differential equation is 9x double prime equals x, or, bring x to the left, 9s squared minus 1 times x equals 0, meaning either x equals 0, the trivial solution, or s is plus or minus 1/3. That means the general solution has to be in the form of a e to the t over 3 plus b e to the minus t over 3. Plugging in your endpoint constraints, at t equals 0, x is 5. At t equals 8, x is 4. Solving for a and b gives you x of t. And since x dot equals u, take the derivative. That's also the input. This is the optimal input to drive you from 5 to 4 in 8 seconds. My cost function is I'm going to weight x squared and u squared. By weighting x squared, notice that I want to come down. That reduces x, reduces the cost, and then come back up. If I change the cost function, like let's, instead of weighting u by 9, let's weight x by 100. What you wind up with is, going through the derivation, I'll wind up with the general form is a e to the 10t plus b e to the minus 10t. Plug in the two endpoints, and I get this solution. By weighting x, I now drive x to 0 very quickly. and then at the end, x comes off 0 to go to my endpoint. Again, this is very common in calculus variations. I'm going to have two solutions, a stable solution and an unstable solution. The unstable solution pushes you up to the endpoint right at the end. Once I get there, I've met my endpoint, the problem's done. Do a third case. Let's do the generalized case where I have a matrix, x dot equals ax plus bu, and my cost function, this is the generalized cost function for a matrix. X transpose qx is analogous to x squared, u transpose ru is analogous to u squared, q is typically a diagonal matrix of positive numbers, that's the weighting on each element of x, r is usually also diagonal. To solve this, do what we did before. Take my function, x transpose qx plus u transpose ru, add a LaGrange multiplier, times my constraint, and bring in x dot to the right, making it equal to 0. I now have three equations to solve. Do the Euler LaGrange equation with respect to x, Euler LaGrange equation with respect to u, and Euler LaGrange equation with respect to m. Gives you three sets of equations to solve. Or, since I have x dot m dot, this is the generalized solution to that problem. This is where the trick comes in. Let's assume m is some matrix P times x. If you do that, I wind up with full state feedback, where the feedback gains kx is R inverse B transpose P. Doing the substitution for m, I wind up with three sets of equations. I have x dot is this, there's my feedback gain, R inverse B transpose P. P has to satisfy this equation. This is quadratic in P. Here I've got a P squared term. This is called the algebraic Riccati equation. If I want to find constant feedback gains, that means that P dot equals 0. The solution to that will be the solution to this. I know A, I know B, I know Q and R. Q and R are my weightings. Q is the weighting on X, R is the weighting on U. The solution to this equation is P. Once I know P, I know Kx, my feedback gain K. So, to solve the optimal control problem, I have to solve a quadratic equation in P. That's called the algebraic Riccati equation. That's a very important equation. Anytime you want to do optimal control, I need to solve it. For example, let's start with a scalar system. X dot equals u, and I have a weighting qx squared plus ru squared. In that case, the optimal feedback gain will just be the square root of q over r. What that means is a couple things. First, that the absolute value of q and r don't matter, only the ratio. So likewise, I can arbitrarily make r equal to 1 and vary q, or I can make q equal to 1 and vary r. All that really matters is the ratio between the two. Also, the feedback gains move as the square root of q. So likewise, when you adjust the gains, you have to be rather dramatic. Increase q fairly significantly to get the feedback gain to change. As an example, if I use specific numbers, let's have x dot equals minus x plus u, and j is just x squared plus u squared. That means that q equals 1, r equals 1. The algebraic Riccati equation then is just minus 2p minus 1 plus p squared equals 0. Gives you two solutions for p, two solutions for k. One of these is stabilizing, the other one makes it unstable. Typically you throw out the unstable gain and keep the stable one. So again, there's always two solutions since this is quadratic. The unstable one you ignore, that's the straight solution. Keep the stabilizing gains. So this is the optimal feedback gain for that scalar system. That's the simple case of trying to find a feedback gain for a scalar system. What we'll be looking at in our next lecture is applying that to a generalized dynamic system that's n by n.